So in this lecture we will be talking about filtering long data sequence. One of the technique, this is called overlap add method. So first we will talk about the overlap add method, its algorithm we will discuss about, then we will consider one example to explain how this particular algorithm works. Let's consider a situation that you are given input data. It's a very long data. Input data is a very long data and which is declared by x of n, and you have an LTI system of represented by h of n of finite length capital M. So to consider that the system is such that its impulse response is finite. Under the situation, we would like to compute the system output, that is a yn. So this is very simple. Just in a single run, you are taking the whole piece of signal x of n, passing through LTI systems, providing the impulse response sequence h of n, another input, and computing linear convolutions to provide the output y of n. That is the process. The same thing you can solve by using circular convolution also, in a DFT method also. So there are several techniques to solve this particular problems. Now come to the practical situation. We have number one condition. We have a situation that in our computer or digital hardware we have digital storage devices. We have a very long data sequence stored. It's a long music signal, and we would like to process the music signals or filter out some of the component of the music signals by a particular kind of system or a filter whose impulse response is h of n, and that's a finite length. Fine. So under that situation, what to do? Basically, we can collect all the signal at once and store in primary memory and start processing the output. Processing to the output, right? So in that case, the main problem is that it requires lot of data to be stored in the primary memory. That means memory size is required is very high at once. Fine. So this is the main difficulty. Sometimes in practical process we might have a shortage of memory, so we can't accommodate a very long data sequence for that case. So this is one situation. Next situations, we consider that real-time streaming data. That means your computer is capturing the real-time data through any one of the hardware ports, or it can capture the real-time online data like online musics, and you want to play back simultaneously. So what to do in that case? Basically, one straightforward way is that you are capturing the whole data first, then start playing back. So this could be the process. But sometimes we are more accustomed with the situation that we are keep on listening the music while it is downloading. So in that situation, this particular overlap add method can help us. Condition is that the system impulse response is of finite durations. Mind it, system impulse response is of finite durations. Under that, we are applying overlap add method. So if it is a filter of FIR kind of filters, finite impulse response filters. So we talked about two different situations where this particular overlap add method can help us to solve this particular problems. One is memory requirement, another is time, downloading time. It can save that complete downloading time, and it can start playing back at the beginning of the signal as well, or it can start processing from the beginning of the signal. Okay, so now come to the point. So what to do? Basically, we will consider the complete data sequence of very long. We will divide into multiple sections of individual frames of data, as already we have seen in case of practical DFT process, and assume that all the individual sections have L number of sample points. It is not necessarily to be that L should be the last frame. We must also have to L number of sample points. It may be less than L as well, but let's say for generalization this is L. So what to do? Basically, we will collect individual frames, pass it through the system. This is basically frame output computation, means LTI system. Pass it through the system and produce a frame output. So individual frame input, individual frame outputs. So this yin is the output associated to the xin. So in that way, we will collect all the frames output. Then we will have a combiner process which will declare the final output. So now in case of overlap add, how this frame output process and combiner process will be carried out, we will see in the next. So this is called algorithm, OLA algorithm, overlap add. So first, this we will call as a pre-processing step. That is, we will divide input data into smaller sections. Of each section carries n number of sample points. Then we will start frame output process. What is this? because as you know basically that these particular output computations can be performed in multiple ways: linear convolution, circular convolutions, DFT. So here we will be solving using DFT because there are some reasons. So now this particular DFT process, what is requirement? The input of the DFT must have same number of lengths. So what are the inputs? Inputs are basically spectrum. Spectrum of what? Spectrum of h of n and spectrum of xin. So h of n has actually m number of samples, but it should be transferred to n number of samples because the final output should have n, because we know why this is. So we have to append zeros. How many zeros? These n minus m number of zeros should have to append at that last. Similarly, xi, l number of samples, to make it a capital N, we have to append n minus l number of zeros at the end. So finally we will have the same length sequence, appending zeros to both the sequences hn and xin. So we will take the DFT of individuals, multiply, and that would produce DFT of the output sequence. After that we will apply inverse DFT to get the corresponding yin of length capital N. So this process will be carried out over all the frames. So what happened basically at the finally we will have to find out the overlap samples, and that overlap samples should get added to produce the final output, and the final output signal number of sequence length should be number of frames into capital L plus m minus 1, because as if we just look back how many number of frames are there, that count into capital L, that is the total length sequence of the input, plus m minus 1, that should be the actual final output durations in number of samples. So this is combiner steps and this is the frame output steps, right? Now come to the example. Say h of n is the finite impulse response filter which has three number of samples, that is m equals to 3, and xn is a full long input data sequence which has total 12 number of samples at the input. Fine. So now we are dividing this particular signal into three parts. Individual parts contains L number of samples, that is a 4 number of samples. So now what to do? Basically for individual inputs we would have individual output that would contain 6 number of samples, because 4 plus 3 equals to 7 minus 1 equals to 6. So now if we start computing for the first frame x1n, this will be taken inside the frame output computation, it will produce y sub n. But how it is possible? We know the process of linear convolutions, we know the process of circular convolutions, we know the process of DFT computations. Whichever you think, you can compute that way as well. Somehow you have to get the output. Fine. So next frame we are considering getting the outputs, and while we are placing the output frames, you can see that we are framing in a same time scale. That means the first frame output, originally input was 4 number of samples, and finally it's extended to 6 number of samples. So additional 2 sample points are get overlap to the first 2 sample point of the output of the second frame, because the output length is 6 and original input sequence length is 4. That's why. So this is the second frame output and this is the third frame output. So now this is the time for combiner block. So what is that? Combiner block will find out the overlap sections and get them added and to declare the final stage of output. What is this? 1 1 minus 2 4. These 4 sample, there is no overlapping, so they are taken as it is. Another 2 minus 4 and 3, they are basically added, they are overlapped to minus 2 and 6, that's why they get added. So this is minus 6, this is 9, minus 5 and 0, these are basically there is no overlapping, so these are taken as it is. And 4 and 3 minus 3, these are get overlapped to 1 and 0, that's why this is 5, this is minus 3, and these are as it is, minus 1 3 minus 2 1. So this is the final output. So this yn is basically the final output, and if we perform this particular process in a one-step solution, what was that? We could have taken the whole sequence at once and whole impulse response at once and passing through a LTI system, performing linear convolution or circular convolution, whatever it is, and computing the output. So that would produce exactly the same result. Now this is the time for matching these number of samples. How many number of frames was there? There were 3 number of frames, 1 2 3, so that's why number of frame equals to 3, and each frame contains how many number of samples? 4 sample points, so this is L equals to 4. So 12 plus m equals to 3, 12 plus 3 equals to 15, minus 1 equals to 14. And if we just come from the fundamental knowledge of linear convolutions, input sequence length 12, input sequence length, and another sequence length is 3, 12 plus 3 15, minus 1 14. That's the output. So this is the way of solving the OLA methods. So the next topic we will discuss about overlap sub method.